So I wanted to take a video here to talk about an alternative method for finding volumes of rotation. And this is different in that we're not doing cross sections. What we're actually doing are what are called cylindrical shells. And what this is it's almost like taking a cookie cutter or a biscuit cutter and coming down on a shape and creating a hollowed out cylinder. That's why it's called a cylindrical shell. This method works best kind of depending on what you're most comfortable with. So if you like staying with respect for X, this is a great method when you rotate around vertical lines. But if you really don't mind integrating with respect for Y, rotating around a vertical line you can do with cross sections. It would just have to be done with respect to Y. But for those who like to do this and stay with respect to X as we rotate around a vertical line, cylindrical shells is going to be what works best. And so the idea of it is we cut out shells, and these are nested much like the Russian nesting dolls. And the radius gets measured from the axis, our center, to the inside of the shell. So our axis at the center of the shell to the inside of the shell is our radius. And one thing you'll notice is if we rotate around a vertical line, the radius always involves x. Now, in the case of rotating around the y-axis, the radius should be x. Well, then the height is going from the x-axis up to our curve. So the closer we are in this example, the closer we are to the center of rotation, the taller our shell should be. But because the height is moving up and down, the height will always involve y. And then the last piece we need is actually how thick the shell is. So the thickness is going to be the change in the radius. And I'm using dr rather than delta r because this being calculus, we want it to be infinitely thin. So an infinitely thin shell means that we're going to use a dr rather than a delta r. So, and that's how thick the shell is here. Now, because r always involves x, dr will equal dx. Now, the idea is we find the volume of this one shell and then accumulate all of the shells. So the way we find the volume of the shell is we cut it open, much like the label on a can, and roll it out flat to get a rectangular prism. Well, for the rectangular prism, the thickness is dr, which we already said is going to be the same as dx. The height is the same. So we'll still have h for the height. But then for the width is the circumference of the inside of our cylinder, which will be 2 pi r, or 2 pi times something involving x. Well, then the volume of just one of these shells, of one shell, is going to be 2 pi rh times dr. Now then, to accumulate, we use an integral of 2 pi rh dr. And then our bounds will be what could the radius be between, because this is with respect to r. So our initial radius to our final radius. And this is the idea of cylindrical shells. So if we do an example here, let's say we have the region in the first quadrant that's bounded by r equals the square root, or y equals the square root of x, the x-axis, and x equals 4. So the shaded area, and we revolve it around the y-axis. So I'm still going to go ahead and try to sketch what the shape looks like. So if I reflect the square root over and then rotate it around the y-axis, I get kind of a bowl shape. It's going to be a weirdly shaped bowl. And what I'm finding is the volume of the bowl itself, not what would fill the bowl here. So then if I'm doing cylindrical shells, it's the idea of I'm taking a cookie cutter and I'm cutting out this cylindrical shell from the middle of my bowl. And again, I personally find it helpful to go ahead and draw the shell off to the side. And here, my height is going from the x-axis up to this the curve. So my height is y, which I know is the square root of x. My radius to the inside is going from the y-axis until I come over to hit the curve. Well, that is actually how we measure x. And I already know that dr is going to equal dx. So my volume is going to be the integral of 2 pi, my radius, times the height, dr. And then I have to stop and think in terms of what could my radius go between? Well, the smallest my radius could be is 0, and then the largest my radius could be is 4. And when I go ahead and evaluate this integral, I get that this integral is 80.425. And there is our volume. Now, if I had gone ahead, I could have gotten this exact same volume if I had done this using cross sections, but I would have had to do that with respect to y, and this would be a washer.